So this is lab 2, AC response of RC and RL circuits. So basically the word response means output. So we'll be looking at the outputs of RC and RL circuits. Capacitors and inductors are frequency sensitive components. So what do I mean by frequency sensitive? If you look at the manual, you will see that the reactance of a capacitance Xc is related to frequency with this formula 1 by 2 pi Fc. If C is kept constant and F is increased, the reactance will vary inversely. That means if we sketch a graph over here briefly, with increasing frequency, reactance of the capacitor will behave like this, a 1 by x graph. And for an inductor, the reactance of an inductor is related to frequency with this formula 2 pi fl. So if L is kept constant and F is increased, the relation between the reactance and the frequency would be something like this, a proportional curve. So as frequency increases, the reactance of a capacitance decreases, and as frequency increases, the reactance of an inductor increases. So we'll investigate this property in a circuit by implementing these circuits. We'll look at one experiment for RC, and we'll look at another experiment for RL. So first let us consider this RC circuit, where we'll analyze the response of an RC circuit. So we have a source of 3 volt peak and initial frequency of 200 Hz, and we have a resistance of 10 kilo ohm and a capacitor of 0.1 microfarad. So the components that we will use are these resistance and capacitance. So we will connect this circuit. If we look at our data table for this experiment, lab 2 experiment 1, we will see that we will need to calculate the practical values or measured values of the resistance and capacitance that we will use. And for the analysis, we will start at 200 Hz or 0.2 kilohertz and increase the frequency up to 2 kilohertz. At each frequency setting, we will measure the peak voltage VR across the resistance and peak voltage Vc, the voltage across the capacitor, and we will observe the voltage drop across these two components and see the effect of frequency. So if our theory is right, as frequency increases, the reactance of the capacitor should increase. As frequency increases, the reactance of the capacitor should decrease. So initially at a lower frequency we expect a higher voltage, and as frequency increases we expect to see a decline, and we should see a lower voltage than we began with at 2 kilohertz. So we'll record the data and see if our theory holds true. So we should now first build the circuit. So if we go back to our circuit diagram, we see a simple series circuit, 10K resistor and 0.1 microfarad capacitor. They are connected in series. But before that, we are going to record the experimental values. So I attach the resistance to the board, and measured the practical values. I attach the resistance to the board and measure the actual resistance from the resistance measurement setting of our DMS. So we have a resistance of about 9.78 kilo ohms. We should record that value in our table. So for the capacitor, we will measure the practical value using an LCR meter. So our value is 0.1 microfarad. So we will place the knob at 2 microfarad setting and then place our capacitor. So we have 0.107 microfarad. 0.107 microfarad is our actual value. So now we will start building our circuit. So as we saw earlier, we are going to implement a simple series circuit where I'll place the resistor and capacitor in series and connect the source to the series network. First I place the resistor here, and then I place the capacitor in series. So we have built the network. So here you see the resistance starts at this node, the other leg ends at this node, and in this node we attach one leg of the capacitor, and this node has the other leg of the capacitor. So from the circuit you see that the common node where we have both the legs of resistance and capacitance is B. So in the circuit this node is B, and this end of the resistor is A, where we'll connect the plus of the function generator, and this node of capacitor, the other leg of capacitor is node 0, where we'll attach the negative polarity or black wire of the function generator. So we'll do that now. So I have attached wires to the clips of the function generator. This is the red wire and this is the black wire. I'll attach the red wire to node A, where the resistance leg sits, and the black wire to the capacitor's node. So our circuit is complete. So we have attached a resistor and capacitor in series and placed the source. The red wire is in this node, the black wire is in this node. For measurement, we'll need to attach our oscilloscope. So we'll attach our oscilloscope to the circuit. So by looking at our circuit, we see that we have two nodes, node A and node B. So we can place two of these channels at each of these nodes. So if we place channel 1 at node A and channel 2 at node B, we will get voltage of A at channel 1 and voltage of B at channel 2. And so we'll see that if we attach channel 1 to node A and channel 2 to node B, we'll find the voltage drop across the capacitor from channel 2, and we can find the voltage drop across the resistance from VA minus VB, which is channel 1 minus channel 2, which we will find by using the math feature of the oscilloscope. So this is channel 1. The black wire always goes to the ground, and we'll attach the positive portion of the channel to node A, which is this end. Similarly, for channel 2, the black wire always goes to the ground, which is the node 0, and this portion, the positive part of the probe, should go to node B, which is this node. So channel 1 is attached to node A and channel 2 is attached to node B. Now we can start recording our readings. So if we go back to our data table, we will see that we have to start at 0.2 kilohertz, which is 200 hertz, and keep increasing at increments of 200 hertz up to 2 kilohertz, and we will have to record both the voltage drop across the resistance and voltage drop across the capacitance. The channel 2 is attached to node B, which will give us the voltage drop across the capacitor directly, because channel 2 is connected to node B and the capacitor is connected to between node B and ground. So channel 2 is actually going to show us the voltage drop across the capacitor, and resistance is connected between node A and node B, which we will have to find by subtracting the voltages of node A and node B, which we can do by subtracting voltage of channel 1 and voltage of channel 2. So I turn on the function generator by pressing the power button, and I turn on the oscilloscope by pressing the power button on top. We wait as the oscilloscope powers up. We see that the output output of the function generator is 20 hertz, and we see that our range is at 1K, and the default waveform is triangular. We shift the waveform to sinusoid because we will need a sinusoidal input, and 1K range is good enough for our task. And if we need to change, we will change accordingly. So first I set the frequency to 200 hertz. Notice that the frequency jumps very frequently, so we will keep a value very close to 200 hertz, but we do not need to get 200 hertz accurately. So now I adjust the oscilloscope. We will do that by first changing the time division so that we can see the curves accurately. We see that the voltage setting is good enough. The voltage division setting, the vertical setting, is good enough because we can visualize both of the curves easily. So channel 1, which is connected to node A, is giving us the input frequency. So channel 1 Vmax is 3.92. A brief reminder that this is the values that are being shown by default, because the previous use of the oscilloscope had these settings. When you turn on the oscilloscope, you may not find these values like this. You can change any value that you want by pressing the appropriate button. So for example, if I want to change this reading to channel 1 voltage peak to peak, I should press this button, or I'll get this menu, and I shall press voltage category. Since I want to make a voltage reading, I choose channel 1, the type is voltage minimum. If I press the type, I get a whole set of options. I rotate this universal rotator to get to the required setting. So voltage peak to peak, it has been selected. Now I can press return. Now you see that channel 1 voltage peak to peak is being shown in this block. So you can get any reading that you want in any of these blocks. So channel 1 is connected to node A, and this is the value of our source voltage. We need to set it to 3 volt peak. So we do that by reducing the amplitude. I reduce the amplitude until I get 3 volts. So this is good enough, 3.04 volt. So we can start conducting our experiment. So our first reading is for 200 Hz, and we already have the voltage of the capacitor at channel 2 because channel 2 is attached to node B. So we can directly record this as the voltage drop across the capacitor. To find the voltage drop across the resistor, we'll have to perform a mathematical operation where we'll have to subtract two node voltages, VA minus VB, which is channel 1 minus channel 2. We can do that by accessing the math menu. We see that source A is channel 1, source B is channel 2, and the operation is minus. So we're getting the desired output by default. If you need to change any settings, you can easily do that by pressing the button corresponding to each of the options. So if you need to change a channel in the source, you can just press the corresponding button. So if I press this button, this became channel 1. If I need channel 2, I can just press this button. The operation is minus. If you need to change the operation, just press this button and you will get a lot of different operators. We will keep it at subtraction because we need to perform a subtraction. Now you can turn this menu off by pressing this button. So if I press measure, we are getting the voltage drop across the capacitor from this measurement, the channel 2 Vmax, and to find the voltage drop across the resistor, which is this new waveform created by the math operation, the purple curve, we can get the Vmax by using cursor. So if I press cursor, we see that the cursor is off. We turn it on by moving it to manual mode, just by pressing this button. The source is math. Since we are going to record the reading of the math curve, the source should be math. It can be channel 1 or channel 2, but to take the reading of the math curve, you should move it to math. To get the value of peak voltage, we should move cursor B or cursor A, any one of the cursor, to 0 volt. So adjust the cursor until you see 0 volt. So I'm using cursor B, so I should adjust the cursor until I get 0 volt at this block. So I have a 0 volt here. To get the peak value, I should move cursor A to the peak of the curve that I am measuring. So I should move cursor A, which is located here, to the peak of this purple curve. So I select cursor A from this button and rotate the knob until it is located at the peak. So I see that the voltage drop across the resistor is 2.32 volt. So from measure, we see that the voltage drop across the capacitor is 1.76, and from the cursor we see that the voltage drop across the resistor is 2.32 volt. We should record these values in our table. So the voltage drop across the resistor is 2.32 volt, and voltage drop across the capacitor is 1.76 volts. Okay, so we have recorded the value for 200 Hertz, and we should keep repeating the same process for 200 Hertz increments up to 2 kilohertz. So our next frequency is 400 Hertz, to get by altering this frequency now. Okay. We got to a value close to 400. We check if our input is still at 3 volt peak. It's still at 3 volt peak, so we can directly get the results. So we see that the channel 2 is 1.08 volt. This is the value of the volt. This is the voltage drop across the capacitor. To get the voltage drop across the resistor, we should adjust cursor A to the peak of this math curve. So we have to increase it a bit. Okay. So 2.64 volt. So voltage drop across the resistor is 2.64 volt. The voltage drop across the resistor is 2.64 volt, and the voltage drop across the capacitor is 1.08 volt. We should record that in our table. We repeat the same process for all the next frequencies. So our next frequency is 600 Hertz. Channel 1 Vmax is still pretty close to 3. I'll alter it a bit to see if we get to 3. Okay, so we have gotten 3. So now channel 2 Vmax is 800 millivolt, and the voltage drop across the capacitor is it's 2.8 volt. So 2.8 volt for resistor and 800 millivolt for the capacitor. Now we move on to our next frequency setting at 800 Hertz. Measure. So input is 3.04, we're good. So channel 2 Vmax is 640. We see that the channel 2 is getting pretty small. To get better accuracy, we should increase the volts per division of channel 2, which we can do by rotating this knob for channel 2. We see that the voltage drop across the capacitor is 528 millivolt. We can adjust the time base to increase the visibility. So 528 millivolt for our capacitor, and for the resistor we should adjust the curve a bit. Okay, 2.88 volt. So 2.88 volt for the resistor and 528 millivolt for the capacitor. We record this in the table. Moving on to the next voltage value. 1 kilohertz. Okay. .96 volt for resistor and 440 millivolt for the capacitor. 440 millivolt for the capacitor. For the next voltage setting of 1.2 kilohertz, you see that okay, so I altered the time division setting and voltage division setting and reset the math function by turning it off and on. So to reset the voltage division setting of the math so that I can get a better reading. So from measure we see that at 1.2 kilohertz the voltage drop across the capacitor is 364 millivolt, and for the resistor we have to alter cursor A to the peak of our math curve and see that it's 3 volts. So we record these values in our table. So 3 volt for the resistor and 364 millivolt for our capacitor. Then we move on to our next set of readings at 1.4 kilohertz. At 1.4 kilohertz, we see that the drop across the capacitor is 308, and for the resistor, we need to adjust to the peak, and it's 3.04 volts. So we record this in our table. 8 millivolts. Then we move on to our next reading at 1.6 kilohertz. At 1.6 kilohertz, we see that channel 2 we have 276 millivolt, which is the voltage drop across the capacitor, and the voltage drop across the resistor remains same, 3.04, and we have 276 millivolts. Now we change our frequency to 1.8, and at 1.8 we see that channel 2 is 252 millivolts, which is the drop across the capacitor. As for the resistor, the value still is 3.04 volts. So 3.04 for the resistor, and for the capacitor it's 252 millivolts. And now for our final reading, we go to 2 kilohertz. At 2 kilohertz we see that channel 2 reading is 220 millivolt, and from the cursor we find that the resistance drop is still 3.04 volt. 3.04 volt for the resistor and 224 millivolt for the capacitor. So we see that, as expected, with change in frequency, with increasing frequency, the reactance of the capacitor should decrease and the voltage drop should decrease accordingly, which we see in the trend in this table. We started at 1.76 volt at 200 hertz and ended at 224 millivolt at 2 kilohertz. And the resistor, as the voltage of drop across the capacitor decreased, the drop across the resistor increased, since according to KVL the loop voltage should remain 0. So we have verified the AC response of an RC circuit. Now we'll look at our experiment 2, AC response of RL circuits. Here, as previous, we will connect a series circuit, but instead of capacitor, now we're observing the effects of an inductor. So there is a 100 ohm resistor, 330 microhenry inductor connected in series, and then we have a source. So we will place these three components in series and connect our circuit. And as previous, there are three nodes A, B and 0, and we will build the circuit according to this diagram. Before building this diagram, we have to measure the practical values of our components. So we will do that using DMM and LCR meter and record them in our table. First of all, I connect the resistor in the breadboard. And use our DMM in the resistance measurement mode to get the practical value. It's 96.6 ohms. Now we will measure the inductor value of the inductor using LCR meter. I turn on the LCR meter. The knob is located at 2 millihenry. At this point, I will connect our inductor with the crocodile clip. We can use either the crocodile clip, or we can use the this portion here to connect our component. So we see that the practical value is 0.335 millihenry, which is 335 microhenry. So it's 335 microhenry. So 335 microhenry has been recorded. Okay, now we'll build our circuit. First, I place the resistance. One leg goes in this node. One leg goes in this node. The other goes in this. Then I connect the inductor. One leg goes in this common node, and the other in this. So I have attached the resistor, one leg in this node, one leg here. The inductor, one leg starts from this node and the ends here. So according to our circuit diagram, this is node B. This is node B because you see the common node where one leg of resistor and one leg of inductor meets is node B, which is seen here. And now we attach the source from our function generator. In our function generator, we have this red wire and this black wire. According to our circuit diagram, we will attach the red wire, the plus one, with our node A, the black wire in the negative terminal, which is node 0. The red wire will be connected to the open end of the resistance. The black wire will be connected to the open end of the inductor. So I am placing it now here. Red wire goes to open end of resistor, black wire goes to open end of inductor. So now we have connected the source to our circuit. Red wire goes here, black wire goes here, and our circuit is complete. Now before moving on to taking readings, we will need to attach the oscilloscope. We attach the oscilloscope. So this is channel 1 of the oscilloscope. The black wire always goes to the ground, and I will attach this positive part of the probe to node A. From the circuit diagram, node A is here with the red wire of the source. So from this channel we will be able to get the voltage of node A, which is the source voltage. Channel 2, I'll connect the black wire to the ground and connect the positive part to node B. Remember, node B is the common node where the resistor and inductor meets. So from node B, with channel 2 we'll get VB, which is the voltage drop across this inductor. So we'll get the voltage drop across the inductor from channel 2, and we'll get the source voltage from channel 1. And to get the resistance voltage drop, we'll need to subtract voltage B from voltage A, VA minus VB. We can do that by channel 1 minus channel 2 from the math function of our oscilloscope. So now we turn on the function generator by pressing the power button, and turn on the oscilloscope by pressing the power button located at the top. So 2 kilohertz is the starting frequency for the function generator, so we don't need to change the frequency. However, the default starting waveform is triangular. We change it to sinusoid. We see that the amplitude is 3.04 volt, which is required at channel 1, which is connected to node A. So if it is not 3.04 volt, we would have to adjust using the amplitude. So this is our required reading, required source voltage. I increase the a bit. So at channel 2, which is located at node B, it gives us the voltage drop across the inductor. So the voltage drop across the inductor is 138 millivolt. I have changed the voltage division to get a better, more accurate reading. For the voltage drop across the resistor, we need to perform math, but before doing that, I adjust the horizontal time scaling to get a better view. By pressing the math button, I see that source A is channel 1, source B is channel 2, and by subtraction we have the math signal, which is the purple signal here. We will measure that value using the cursor. So source should be math, cursor B should be located at 0 volt, which is the case. We adjust the cursor A to go to the peak. .96 volts. So at 2 kilohertz, the voltage drop across the inductor is 138 millivolt, and that of the resistance is 2.96 volt. We record that in our table. Then we increase our frequency to 4 kilohertz, our next reading. we decrease the volt per division of channel 2, which had gone out of scope. Now we see that the voltage drop across the inductor is 244 millivolt, and that of the resistance is still the same. So we record this in our table. 2.96 for resistor and 244 millivolt for the inductor. Now we move on to 6 kilohertz on the next reading. We have 6 kilohertz. I adjust the horizontal knob. We see that 340 millivolt is the voltage across the inductor. As for the resistor, it's 2.88 volt. Okay, so 2.88 volt for the resistor, and for the inductor it's 344 millivolt. Then we move on to 8 kilohertz, our next reading. I cannot go further because I have reached the maximum output frequency output for this range, so I reduce the knob down and press the 10K button. It's 14.2K. I reduce a bit and get to our 8 kilohertz required frequency. Channel 2 has gone out of scope. I reduce the time division, voltage division to get it into scope, and we see that the voltage across the inductor is 472 millivolt, and that of the resistor is still pretty close. Is still 2.92. So we readjust the amplitude a bit. Okay, so we see that the voltage drop across the inductor is 464 millivolt, and that of the resistor is still 2.88 volt. So 2.88 and 464 for our inductor. We move on to our next reading at 10 kilohertz. We set the frequency to 10 kilohertz. Adjust the time division a bit. The voltage drop across the inductor 560 millivolt from channel 2, and that of the resistor is 2.8 volt. 2.8 volt for the resistor and 560 millivolt for the inductor. We move on to our next set of readings at 12 kilohertz. Okay, so we see that the voltage drop across the inductor is 680 millivolt, and and that of the resistor is still 2.8 volt, and we record that in the table. Then we move on to 14 kilohertz, our next reading. At 14 kilohertz, we still have 2.80 volt at the resistance and 760 millivolt at the inductor. Then we move to our next reading at 16 kilohertz. We adjust the channel to get channel 2 screen in scope. So now we see that the voltage drop across the inductor is 940 millivolt, and that of the resistor is 2.76 volt. So 2.76 for the resistor and 940 millivolts for the inductor. So we go to our next frequency at 18 kilohertz. So at 18 kilohertz we have 1 volt at the inductor and 2.76 still at the resistor. So we move on to our last reading at 20 kilohertz, and we see that the voltage drop across the inductor is 1.14 volt, and that of the resistance is 2.72 volt. So 2.72 for the resistor and 1.14 volt for the inductor. So we have tabulated all the required readings, and we see that as the frequency increases, the voltage drop across the inductor increases, as is expected from the theory, where the reactance of the inductor increases with frequency. So correspondingly the voltage drop increases.